Right, so we've just been looking at a whole lot of different solids or substances, because they might not be solids at room temperature, like water is one of our examples, which we know darn well is a liquid. What I've just given the class are 10 different substances, and they're either ionic substances or they are molecular substances, and asked the class to work out how to do it. So how to, what they are. And what we're going to go through now is actually the way that we can confirm whether you're right or wrong with those answers. So to link this to the work that we've done already, we have been looking at these 4 different types of substances or solids. Now metallics are quite easy to work out because they are elements on the periodic table that are the left-hand side of that line that goes down in steps. Right, so there are things like Fe, Al, K, Ca, etc. So they are single elements. That's how we know that they are a metal. If they were a non-metal, then they would have to be molecular, with the exception of carbon, which we know is a covalent network. So the allotropes or types of carbon are our covalent networks that we learn about, as well as silicon dioxide. And those are the only ones we actually learn about in this year level. That leaves ionics and moleculars. Now moleculars are normally quite easy when they're elements. So the non-metallic elements, like fluorine, like sulfur, like hydrogen, are going to be molecules because they're non-metal bound to a non-metal. So things like H2, so you notice there needs to be more than one of the atoms. There has to be a covalent bond between the atoms. Okay. Cl2. Sulfur is technically S8. And it has different allotropes or different shapes of that as well that are different colours that we don't learn about this year. It's not things like helium or argon or neon. They're just atoms and they don't come under these categories. Okay? But molecular can also be things such as water. A non-metal bound to a non-metal. It can be things that are a semi-metal bound to a non-metal as well, and things like that we're going to look at. That's where it gets really confusing. There has to be a way to decide, is it going to be molecular or ionic? And this is particularly true with the semi-metals, the things nearest that jagged line on the periodic table. Just to put another couple that we've got in our thing that we were doing, we had CH4 in our lot. We had, what else will I put up there? CO2. Right, so those are our molecules. Inside the molecules we have a covalent bond between the atoms. I'll explain that a bit more in a moment. Ionics, again, are made up of more than one atom bound together, but the difference here is that they've become ions. They've lost or gained electrons. And I've done ones that are only made up of what we call monatomic ions, atoms that are made up of ions that are made up of one atom only. But you can have things like sulfate, nitrate, those sorts of things, some more complex ions, and they're easy to pick. What I'm trying to get you to look at in this part of the unit is the stuff that, it's hard to tell, is that a metal or a non-metal? I can't remember. And is it bound to a metal or a non-metal? I can't remember. So how to work it out using a periodic table. Some of the examples that I've given over there are things like NaCl. Sodium is actually a metal even though it's soft. Chlorine is a non-metal. So if we bind a non-metal with a metal, usually, not always, usually this will make an ionic bond. Okay. Other good examples that we've done, magnesium oxide, and I'm being very careful with my selections here because there's a couple there that are confusing. I'm going to put one that's not on our board over there, copper sulfate, one that we've met a few times. Okay. So the trick is, how do I know if something is ionic or molecular? Because that's probably our hardest one to focus on. How do I know? Well, there's one generalization that's really easy to remember, and it is a rule that can be broken. So it's only a starting point. The first thing you look for is, for an ionic compound, you're looking, is it a metal bound to a non-metal? Okay, metal bound to non-metal. It's a general rule, it's not always true. Okay, but basically if it's a metal and a non-metal, you would infer immediately that's ionic. You still need to confirm it, but you would infer that to start with. So therefore, molecular must have something slightly different about it. And if we ever look at that, they're all non-metals. So it's a non-metal plus a non-metal. Okay, so we've got our nice starting point, but it's not actually good enough. What we're really trying to look at is the bonding between those things. I'm going to take sodium chloride as an example. Now, if we have sodium as an ion, it has a 1 plus charge. And if I have chloride, which is what we call chlorine when it's become an ion, it's a 1 minus charge. So there's actually been a transfer of electrons, of valence electrons. This one's got an electron configuration of 281. Its 1 has been lost, and because there was a chlorine atom nearby that was 287, it's picked it up to become 288. So this has got an electron configuration of 28. This is 288. Why are these magical numbers of 8 at the end? What's so important about those? Fantastic. So if that wasn't heard on the video, full valence shells. Okay? That's why ions form, to become electrically stable. So they have full valence shells, or outer shells, or empty in this case, because its third one's disappeared. This means that there is a really strong attraction between these. And what do we call that very strong attraction between these? This force between these ions? Ionic bond. Okay, so this is still linking it to the stuff we've done before. This is called an ionic bond. Okay. Now I'm going to jump over to the moleculars. And I'm going to grab water because it's one that I like using as an example. In this, hydrogen has an electron configuration of 1. Oxygen has an electron configuration of 2, 6. And there's another hydrogen, 1. So what happens is, this one electron goes in between the two of them, and this one does as well. And it gets shared between the hydrogen and the oxygen, and between the hydrogen and the oxygen. So I end up with, whoops, I'm going to use red for showing bonds, this. This ends up being 2, 8, and actually 2 of these electrons get shared back. So this one ends up being 2, 2, 8, and 2. 2 is our first valence shell, so that's full. Okay? By being shared, they both get to use those electrons for a period of time. So all of them have full valence shells. But because there's sharing involved, it's a bit like if you get to share money. You both might be able to buy something nice that you can both use, but if one of you took all the money, you'd get it for yourself, and it's a much stronger connection with whatever you bought. Whereas if you both shared the money to get something, you've got to both use it for some time each, so your connection to that item you bought isn't quite so strong. Okay? Likewise, this isn't such a strong bond. It's still strong. These are going to hold on to each other pretty well. And this is called a covalent bond. So, what we're seeing is a big difference straight away. Metal and non-metal generally. Non-metal and non-metal generally. Ionic bond versus a covalent bond between the atoms. You could argue this is an ionic bond between atoms, but you have to say it's between ions. Okay? So how do I know if something's going to make an ionic bond or if it's going to make a covalent bond? Because that's what's really, really important. How do I know if it's an ionic bond or if it's a covalent bond? And for that we need to look at a thing called electronegativity. Okay, and electronegativity, I will put this definition up, but I want to say it first. Electronegativity is a measure, and it's a relative measure, so it's just a scale that we've made up. Okay, it's the relative attraction for the bonding electrons. Okay, so it's an atom's or a nucleus's attraction for bonding electrons. Fluorine is what we call the most electronegative element that there is. So we give it a 4 out of 4. 4.0 is its electronegativity. There is not a single element that we know of that has more attraction for bonding electrons. It will basically rip electrons off anything to make a covalent or an ionic bond with it. Okay? It is the most electronegative element. Conversely, things like cesium and francium down the bottom left-hand corner of the periodic table have really, really low electronegativities. They actually don't have much of a pull at all. It's around about 0.4, I think. They have very little pull on valence electrons because basically it's so far away. There's so many electron clouds before it's the valence ones. It's too far away from the nucleus. And so there's a really weak pull. So if they come nearby another element, they tend to give their electron away. They'll either give it away or share it because the pull, the relative attraction is so low. So electronegativity is a measure of how strongly an atom attracts bonding electrons, okay, or outermost electrons. So how do I use electronegativity to answer my original question? Is it an ionic bond or is it a covalent bond? Well, every single element has a unique electronegativity value that is given to you in your book. So if you have a look, we're using beginning chemistry. If we have a look in there, sorry I didn't have mine open ready to show you quickly, on page number 125, put that there for us for later, page 125. Then it has the values for every single element on the periodic table except for the radioactive ones. Okay. And you'll notice there's no value for the noble gases. That's because they generally don't bond with anything. There are a few exceptions you'll learn about next year, but for this year they don't have a value for that reason. If I have a look at sodium, what's its electronegativity according to that table? 0 point something. 0.9. Okay. So sodium's is 0.9. What about chlorine? 3.0?
Yeah.
Okay. What is the difference between those two numbers? 2.1. Okay. So, sorry, a bit of maths coming in here. In maths, the little triangle is how we, without a computer, write delta, which means difference. Big E, big N means the difference in electronegativity, which means the big one minus the little one. Yep. So the delta En in this bond is 2.1. And I've already said it's ionic, so that must be a big enough difference for electrons to be ripped off. Sodium isn't holding onto its electrons hard enough, so it loses them to chlorine, or just one of them actually. Loses its electron to chlorine to make it 2,8, 8, and make this one 2,8. This is what we call a big electronegativity difference. However, if I go over here and I have a look at these electronegativities, what is hydrogen's?
3.1.
2.1? Okay, and what is oxygen's? 3.5. So the difference of electronegativity here is only 1.4. So I write that as delta E N equals 1.4. Obviously that is what we call small enough to be called a covalent bond. Only just, by the way. It's only just small enough. If it was 0.3 bigger, this would be ionic. Okay. However, there is actually a bit of a difference there. And what we're going to get to tomorrow is talking a little bit about polarity. This is what we call a polar bond, because that's still quite a big number. Anything 0.5 or bigger is considered a big number. So this creates what we call a dipole. The electrons are actually attracted more to which one do you think? Oxygen or hydrogen? Look at the definition. Oxygen, because it's got a higher electronegativity. So it creates a thing called a dipole. Whoops, wrong colour. Sorry. So it creates a thing called a dipole, or a pole. Okay, it's creating a vector in that direction. And both of these bonds are doing that. If I was to show this in 3 dimensions, it would show why water is what we call a polar solvent, but we'll get to that much later in the unit. Okay, So we end up with what's called a polar covalent bond here. This one here, though, is big enough to be called an ionic bond. So what about, how do I get a covalent bond where they are shared pretty much evenly? How would I get... This one's not shared evenly. Oxygen's looking after the electrons for a longer period of time than hydrogen. This is why it's called polar, because it means the negative electrons are around the oxygen a bit more than they're around the hydrogens. Okay, we'll get to that in more detail later in the unit. How do you think we get one? You know, you notice the number's gone down from ionic to polar covalent. What do you think happens to that number if we have just a non-polar covalent bond where they're shared evenly or very close to evenly? Do you think the number goes down or up? Down. So, of course, if anything's bonding with its own element, H2, Cl2, those sorts of things, they will be non-polar. Because the difference would be what? Any number minus itself is 0. So they're what we call pure covalent bonds. There's no difference in electronegativity. The bonding is even. I'm going to grab CH4. I put that one there for a really good reason. And use that as my last one. Hopefully this fits in the screen. Now hydrogen we've already used, and this one is 2.1. That doesn't change, so I'll keep that. So all of those are 2.1, but they're not bound to each other. They're bound to carbon, which is 2.5, I believe. Just double check that I'm right. Yep, cool. So the carbon is 2.5. So my electronegativity difference in this one is equal to 0.4. All good with that? 2.5 minus 2.1. That number is so close to 0, that we say that it is a non-polar covalent bond. The electrons spend just as much time around carbon as they do around hydrogen. It's not technically true. Which element do you think they spend just a little bit more time with? Carbon. Perfect. You guys are getting this brilliantly. Okay. So, there are some magical numbers here, and I'm going to put them in red because it makes it easier to stand out. 0.4 is the biggest difference you can have and still call it non-polar. This is the biggest difference you can have. 0.5 is that tipping point where we say, actually now we're going to call it polar. This is really close to what we call ionic. There's a little zone between 1.5 and 1.7 where you need to look at the properties. Conductivity as a solid, conductivity when molten, melting points, boiling points. You need to look at those things we did last week to decide if it is ionic or covalent. Because it's a grey zone. It's like, well, I'm not sure. But basically, the magical numbers are this. Non-polar covalent is less than 0.5 for the difference. Not less than or equal to, less than. Ionic is greater than 1.6. But between 1.5 and 1.7, you need to look at other properties. Melting points. If it's got a very high melting point, but its electronegativity difference is 1.5, you'd probably suggest that it's ionic. Especially if it conducted electricity when molten. Okay, so when you get that 1.5 to 1.7 is a bit of a grey area. Okay. So it's been a pretty big overview of where we're going with this week. Are there any questions before I turn that off? Okay.